So the last speaker of this session before our break is Pierre Martinon from INRIA. Pierre is one of a writer of Book-Up, an optimal control solver, which we have used very efficiently for making people run and modeling running. So I'm a Book-Up fan.
Thank you, Amandine. So, as you said, our team works in optimization. We are not specialists of sports or anything. And we have worked, for instance, on optimizing things from airplanes to hybrid cars or microscopic swimmers. But today, I will say a few words about work about runners. So, more precisely, it seems that in the world of athletes, there is some kind of general feeling that the lane, in French couloir, in which you are, will have an impact on your performance. And people seem to agree that the best lanes are the interior one, in the middle. Then you could run on the exterior, and the worst case is when you are at the interior. And why? There must be some reason. And apparently, this kind of preference is explained by two distinct phenomena. First is just the effect of the track curvature. It's harder to run in a curve than on a straight line because you have to fight the centrifugal force. So this would explain why the interior lanes are bad, because you have a higher curvature, so it's harder to run. But then it would be best to be on the exterior, which apparently is not the case. And it seems that this is explained by the second phenomenon, which is interaction between runners. More specifically, it is generally accepted that you run faster if you have someone just ahead of you that you can chase. And this kind of thing can happen more easily if you are in the middle, because you have more neighbors. And so it seems that the conjunction of these two phenomena make it better to run in the middle lanes. And so our question was, can we find some mathematical model that would confirm this kind of feeling? So that's what we are trying to do. Here, a disclaimer. This is an extremely abstract model of a runner. The previous talk gave great details about the human body with all these bones, muscle, joints. Here, it's a little more simplified. We have a point, which is a runner. So it just has a distance, a speed, an acceleration, and forces. So here we ignore all these complicated phenomena about the feet, the arms, the special movements. And the question is, with that very simple model, can we capture this effect of the lanes? So the equations are very basic. You have distance, speed, acceleration. The control is the force of the runner, and you have some resistance from both the air and the ground, modeled by this coefficient tau. You have some kind of energy reserve that your runner will expend by running. The higher the force, the more energy it will spend. And you recover some energy by breathing. This is the sigma parameter. A few technical remarks that maybe are not that interesting if you are not into optimization. But the key point is that in the end, we want to solve an optimal control problem. We want to find some force along time that will give you the minimum time to run your track. So in the following, we will give some example about a 200-meter race. We use a solver Book-Up, which is a generic tool for solving optimal control problems. And here we take this specific runner, which has these parameters for tau, energy, and force. A small remark, if you are familiar with running, you'll see that this runner is actually very good because he actually beats the world record by a small margin. But here we are mostly interested in the effect of lanes, not the time by itself. But don't be surprised if you see a time better than the world record. So the first of the two effects is curvature. So this is a pretty physical parameter. Your usual 400-meter stadium has this kind of shape. You have two straight portions and two half circles. You see in red, for instance, the staggered starting point, because the runner will start with some kind of shift, so they arrive at a straight line just together. And so when you're on a straight line, you have no specific problem. You just run forward. When you're on the curvature, you have to compensate for the centrifugal force that will push you outwards. And so the runner has to spend some of his force to stay in his lane. So this is a basic expression here, and we choose to model this centrifugal force as some kind of a reduction in your maximum force. If you recall, maximum force here is one of the parameters of the runner, and here we say that when you are on a curve, it will reduce your maximal force. One interesting point is that you see that this phenomenon will have different impact depending on the runner. a runner with a low force will be more affected than a runner with a very high force. This may seem strange because you may think it's just the track, but apparently among runners, some of them say that they are more affected by curvature than others. So it seems consistent to keep this kind of dependency. So here we just show the same runner, our ideal champion, running on a straight line. This is the blue time here at something 18.25. And then on each lane from 1, which is the interior lane, and 8, the exterior one. What you see is the expected effect. You are slower when you are on a curve, and the more you are on the interior, the higher the curvature, and the worse your time is. There is some kind of gap about 1.15 seconds between the interior and the exterior lane. And yep, I can show you if you want. I can try. Here, this is the exterior lane, so you are slower than the straight line, but it's better than the interior lane, and you have something like 0.15 seconds between the two. This seems consistent with the previous paper in the 80s that, using a different model, found 0.1 second of gap. So here you have the speed profiles. You see that when you have to fight against the curvature here in the first half, which is a circle one, you are slower when you have lots of curvature, and you can recover some speed after, but still, your overall time will be larger. So the first part seems okay. If you run on the interior, you're slower, that part is clear. Now, the second phenomenon is about interaction. When you have someone running just ahead of you, you can think, I don't know, these running dog races, when they have some kind of rabbit on the side, we are supposed to go faster. I leave the explanation behind. It would be a very interesting topic, but that's not the point. And here we choose to model this as a reduction of the resistive forces. When you have someone, say, 1.5 meters just ahead of you, you will have less resistive forces. This is a bit maybe from the car races, where you have some kind of aspiration phenomenon, but we kept this kind of formula. It may seem like a very small effect, but when you apply it, here on a straight 200 meter line, you find an increase about half a second, which is quite significant. And apparently, this kind of order of magnitude is consistent with what people in the field say. So it's a small effect, but it has a great impact on your final time. We could, of course, improve this mechanics by, for instance, disabling it when another runner is just passing you. Technically, you would have some kind of time before you realize that you have been passed over and you catch on. So an extension will be to disable this effect if you have just been passed by. And there you have some kind of delay problem if you are interested in that kind of optimal control problem, which I will not detail further unless there are any questions about that. So in straight line it works, you get faster, and now the question, when you put both the curvature effect and the interaction, what do you get? So that's what we do here. So in the black, you have the previous curves about the lanes, and now we have two runners. We have the same runner competing against himself, and we test all possible combinations for the two lanes. And so what does this graph show? For lane 1, so your runner is on lane 1, and we put a second one in all possible lanes, so 2, 3, etc. You have 7 races, and we take the average time. So it's the same for every lane. You have the average with the 7 races with your opponent in all possible lanes. And here, finally, we see what we expected to find, namely that the best times is not in the exterior, it's somewhere in the middle, around lane 6. Then you have the exterior, and the worst is the interior. So it's pretty good because the model was very simple, and still we can find that the best part is not the exterior, it's somewhere in the middle. It's not perfect because if you remember the beginning, people were more keen to be on lane 4, 5. So here it's a bit shifted to the exterior, and we think this is because we can improve the interaction model. For instance, here we have only 2 runners, so you can have only 1 person to chase. In a real situation, for instance, if you are at 5, you can have neighbors on your left and on your right, so you could benefit from more interaction. And also, a second effect is that here it's just a distance forward, but it does not take into account the lateral range. And probably you are not as attracted if you have a runner far away on your side. So interaction should probably take also the lateral distance into account. And we think that if we put those two things together, it will improve slightly the lanes in the middle furthermore. But still, it's pretty consistent with what people say, and it's nice to have this with a very simple model. So to conclude, we are some ongoing improvements, trying different shape of stadium, because it's not as standardized as you might expect. You can have some slight variation in the shape to improve a bit the interaction. And some further work would be to simulate more than 2 runners. Obviously, the best would be to have 8 runners against each other. And the second part is to calibrate the models with actual data from real people, because here you have to set it by hand, which is not so accurate. Thank you.
Thank you very much. We have time for one question before the break.
How do you calibrate the parameter of your models? F max, I don't remember, but there's other one. E max.
Yeah, as I said, it's an important question. Technically, you should have to perform some parameter identification. So this is a continuation of a previous work with Amandine and Frédéric Bonans, and these parameters come from these previous works. So it's, we had some measurements, perform some identification, but actually you can find different set of parameters that will give you the exact same final time. So yes, here you have quite some degrees of freedom, and that's a good question. And you would need to typically to have a runner perform several races on each lane, maybe 10 of each to have some kind of consistency, and then you could fit your model. Ideally, you start by a straight line, so you don't have the curvature effect. You have only, for instance, the maximal force on energy and toe. Then you add the curvature to fit, to refine a bit more. But yes, there are several stages of different kind of models. And last, you would add the trainer, which is the second runner, and you can also calibrate the interaction parameters. But yes, for now, it's mostly by hand, and we try to have some consistent results. But yeah, what it shows is that you can find parameters that will give you some sensible results.
Thanks for the presentation. Is it possible that your model represent asymmetry in running? As I've read that, forgot his name, Usain Bolt, was running with really large difference in contact times for the left and the right foot. Do you think it's possible to represent that in the model and to help trainers or runners in having better symmetry or asymmetry to get to the optimal time?
Yeah, that's a good point. Actually, Usain Bolt was one of the runners I mentioned who said he's particularly sensitive to curvature effects. Regarding the left, right, foot, etc., this is, for instance, for now completely ignored in the model. We could do it, but it would make the dynamical system much more complicated. So the question is it the most significant approximation yet? Because the model is very approximate, and I suspect there are more significant effects to be added first. And then you could move on. Because the question is, how much will this kind of phenomenon impact? Is it 1%? If you have, I don't know, 5% for a different reason, you won't see it until you have found all the other reasons. But yes, all this kind of thing is completely ignored. Same as, for instance, the position inside the lane. It's known that runners don't run in the middle of the lane. They run, of course, on the interior at something like 30 centimeters because they gain a little bit here. This is ignored too. So yes, we still have lots of, actually it's surprisingly complicated and you have lots of things to put. But yeah, here we wanted to focus on 2 broad points to start.
If I may, I would like to add something, is that runners always run in the same, is either clockwise or anti-clockwise, now I don't remember. But one experiment would be to ask Usain Bolt to run the other direction and measure whether the contact times are the same or very different from running in one way and the other way. What I believe is that, as Pierre said, he always says that he has to work a lot against this curvature effects. And so in order to do that, he's bending a lot. And you can see it on the video that he's bending much more than an average runner. So because he's bending a lot, of course, he's going to have different contact times to be able to keep his equilibrium. So to do that, you have to, the model relies on Newton's law of motion. In order to compute performance, we project the law on the x direction. If you want to have a complete model, you have to project it on all directions. And doing it is really possible, and I think you will find both the optimal angle depending on the person, on his strength, on his size, and on the height of his center of gravity, and you will be able to get information of that type. But I think that this type of information will have more influence on the way he runs, whereas here we kind of identify the runner to a point and try to understand when he speeds up and when he slows down in some sense. So maybe we can go to the break and resume at 11:25. Let's thank all the speakers.